So when we have one numerical variable and we're interested into summary statistics, we more often than not look into the central tendency or the location. So where are the values concentrated around? And for this, we typically use one of three statistics: the mean, the median, or the mode. The median is what we all understand as the average. So we just take all the observations over here, sum them, and divide by the total number of observations. That's what we call the mean, which is represented like this, the X and a bar on top of it. And it's often used as, a way to estimate what is the mean in a certain population that these data represent. The problem with the mean is that it's very sensitive to outliers. So if we have, for example, in our case, and we're interested in the price of the listings, then if we have very expensive listings, just a few of them, it's likely that just having those observations are going to skew the mean towards one side or the other. They're going to bias the mean. If we want to prevent that, we can use the median, which is essentially the point that separates all the observations between the lowest 50% and the highest 50%. So we can sort all the observations from the minimum to the maximum, and then we choose the midpoint, that is the median. And the good thing about it is that it's less sensitive to those outliers. So for example, in our case, we have that the median price is 50 euros per listing, whereas the mean we saw it was 65. So that means there are certain listings that tend to be overpriced, probably, because the mean is larger than the median. And then, of course, we can also use the mode, which in our case would be which is the most frequent price in the data set. Now, for numerical variables that have, so to speak, a very high resolution, it doesn't make a lot of sense to speak about the mode because it's very unlikely that we have more than 1, 2, 3 observations with exactly the same number. But for something like this, in which we're talking about euros, then sure, in our case, the most appearing price in the listings is 50 euros as well. But if we're measuring something with very fine resolution, it's very unlikely that we're interested in the mode because it just happens once or twice, maybe out of millions. And so use this mode only if you had very few different values. Then it could tell you something. Again, more often than not, we use the mean. And so when we're talking about the spread of the data, the dispersion, so not only about what it tends to be, but how variable it is. We are usually talking about the range, the minimum, what is the maximum, what is the difference between those 2 points, the maximum and the minimum. But usually you speak about variance or standard deviation. The variance is defined as the expected squared deviation from the mean. So if we compute the mean and then we take distance between every observation in the data set and that mean, then we square it and we just compute kind of the average of those squared distances. So we represent it with S squared, and it's again the squared distance of every other observation from the mean, just divided over n minus 1. By the way, the reason we use n minus 1 has to do with biased estimators. We're not going to talk about it, but it's just providing a better number. And so this square magnifies large deviations. So again, it's kind of sensitive to outliers. If we have a very, very, very large deviation in one observation, that deviation, because it's squared, is going to make that difference very large. And so it's going to tell us that there is a very large variance. And most importantly, it's going to make all of the deviations positive. So in the end, we have a total amount of variation. Two things to know about the variance is that the magnitude depends on the scale of the variable. So if we have, imagine the same distance measured in millimeters, then we're going to have a different variance if we measure it in meters or kilometers, because the numbers are, well, just a lot bigger or a lot smaller, even if they are measuring exactly the same thing. And so mathematically speaking, again, if we have a certain variable x and we multiply it by some constant a, so for example, if we go from meters to kilometers, then we are dividing by 1000, then the resulting variance is going to be multiplied by the square of the constant. So you see, it depends on the units of measurement. However, it does not depend on the location. So if we have a certain variable and we always do plus a certain constant or minus a certain constant, then the variance is the same, because the amount of variation doesn't depend on whether the data are here or there. It's just the same. Now, the problem with the variance is that it's squared. So the units are squared. If you're measuring something in kilometers, then the variance is kilometers squared, which is kind of difficult to understand, right? And so typically what we do is we report the standard deviation, which is just the square root of the variance. And so in this case, we are reporting a quantity that it's in the same units as the variable itself. So in our case, we have a standard deviation for the price of 99 euros. And that's easy to understand because it's in the same units as the variable itself. It's in euros, not euro square. Anyway, a lot of the times we use variance because it has nicer statistical properties, but typically what you want to look at is the standard deviation, especially if you want to report dispersion in a numerical variable. And so many times we're also interested in more rough cut points, so to speak. And we talk about quantiles, which are essentially cut points that divide all the observations, the whole distribution, in intervals of equal probability. So for example, we talk about the pth quantile, like the third percentile, the second percentile, first percentile, etc. And that's telling us what is the point that is dividing the data set in the lowest 1% or 2%, 3%, and the rest. And so this is especially useful to get a sense around the extremes. So what about the top 1, 2, 3, 4%? What about the bottom 1, 2, 3, 4%, or maybe 10%, 5, 25, up to you. So for example, in the case of the price, again, we could be interested in reporting just the point that divides the data into the bottom 5%. That's what that 0.05 corresponds to, and the rest, the 95% of the observations. And that is 23. So 5% of the observations have a price less than 23 euros. Or we could be interested in the opposite. So finding the price, in this case is 137 euros, such that 95% of the observations, in this case the listings, are lower than that. So only 5% of the listings have a price larger than 137 euros. There's something called the interquartile range, which is just quartile 3 minus quartile 1. So if you get the middle 50% of the observations, what is the range? Where are they? So in the case of the price, again, we're talking about 40 euros. And that means the difference between the bottom 25% and the top 25% is 40 euros. So within those 40 euros, we concentrate 50% of the data. And finally, we have the coefficient of variation. And the good thing about it is that it doesn't depend on the units. So it's computed as the standard deviation divided by the sample mean. And what this is telling us is how much variation, how much dispersion there is in the data relative to the mean, or in mean units. For example, the price here is 1.53. So just like the standard deviation is telling us about something like the expected distance between any observation and the mean, what we have here is that the expected distance between any observation and the mean, but in terms of means. So about 1.5 times the mean away from the mean. So that's what this is telling us. And of course, we can look into different charts, different plots. The most typical one is the histogram. And it looks a lot like a bar plot, but it has several differences. So first of all, what it does is here in the x-axis, it takes the whole range of data and it divides the data in different bins or different buckets. So here's one bin, here's another bin, another bin, another bin, etc., etc. So here we have bins of around, I would say, 150, maybe 150 euros. And so what this is doing is counting along the y-axis how many observations do we have in the dataset that fall under each of these bins for the values of the variable. So this is telling us that around 4,700 or 800 are in this bin from 0 to, I would say, 150 euros or so. And then something like 150 observations are in the next bin from 150 to 300, something like that. And so, first of all, why is this line over here spanning up to more than 4,000 euros when it looks like all the data go up to here? Well, that is because we do have observations in there. It's just that there's so few that along the y-axis we don't see anything. So that means there's some observation over there, maybe over there, over here, we don't know. The point is there's just so few that we don't see them. And so what we want to do is make a plot better, right? We're going to see later. And then another thing that this might be telling us is that most of the points seem to be concentrated around 0. That means there's low entropy. So it looks like all the listings have a price that tends to be less than 100 euros over there. So it looks like there's only one price maybe that is happening very often. Maybe we have many prices and it just happens that they are all less than 100, but there are many different prices. We don't know. So this is all hidden in a histogram. If we want to have a better picture of it, we are going to have to tweak it just a little bit. Let's see. So over here we have the histogram. The first thing we could do is just, make the bins smaller so that we see a finer detail of what the distribution looks like. And so what we see here is that the mode, which appears to be around there, it's actually not at the lowest price. So we see some prices over there, about 500 observations that are less than, let's say, 30, 50 euros or something like that. And then we have the mode. So in the previous plot, it looked like the lowest price was the mode. But if we take a finer grain, we see that no, it's not. What else can we see? Well, if we want to, we can adjust the scale. And so instead of going up to 4,000 observations like we did before, we can just go to 500 and it looks like this. And we have a much nicer picture of what the histogram actually looks like. So in this case, we have only 15 observations that are larger than 500. So very often what we can do is just, mention that and then remove them from the plot and just, take a look at the bulk of the data, which in this case are these almost 5,000 observations from 0 to 500. We could even cut over here, makes sense. So we can zoom in, so to speak. And it's a very nice idea to play with the number of bins or with the size of the bins because, sometimes they reveal patterns. Like in this case, if we go from a bin of 25 units that we have in here to 5 units only, then we see there's something funny going on with the histogram, right? It looks like we have some data going over here and some data coming over here. And what this is telling us actually is that most of the data have a price that is a multiple of 5. So something like 25 euros or 30 or 35 or 40 or 45, but not in between. So it's very unusual to have a listing with a price of, 47 euros. They go for either 45 or 50. And we see this over here in this shape. So it's a nice idea to play around a little bit because just by doing that, you might be able to get some new insight into the data just by looking at the plot. And there's something like the next version of the histogram, which is called the density plot. And what it does is essentially smooth the histogram. So instead of looking at bins of data, what it's going to do is make those bins really, really, really small, infinitesimally small, and then show us a nice line, a nice curve of what the histogram would like, what the distribution of the data looks like. And it's doing this by building a model. So underneath the hood, what we have is a statistical model for what the data looks like. I'm not going to talk about it, but just know that we are making a certain set of assumptions when doing this. And so over here in the data set, we have two variables, the longitude and the latitude. for the listings in Berlin. Here are the histograms. Maybe we can get a better visualization by looking at the density plot. What does it look like? Something like this. So it's essentially a line telling us, again, in the x-axis, we have the different values in the data set. And then over the y-axis, we go high if we have data that occurs very often, and we go low if the data don't occur very often in that range. And so you see it's like a histogram, but a little bit nicer, a little bit better picture of what the data really look like and more fine detail. And so something interesting here, for example, is that we have a certain bump in there and a certain bump in there, which is something that we completely missed in a histogram. So it's very useful to plot the two of them together. So for example, the histogram and density plot all together to see a rough, a picture of what the data looks like in a histogram, and then the line of the density to kind of show what could be a model or what could be the reality that the data are representing. And so in the density plot, we can configure a parameter called the bandwidth. So just like we had the number of beans or the bean width in a histogram, in the density plot, we have the bandwidth. And what you need to know is that a high bandwidth is going to make smoothing even larger. So the density plot is going to look even smoother. And if you decrease the bandwidth, it's going to lower smoothing, so it's going to have more peaks. We're going to see an example now. So the thing to know is that when you make a density plot in some software, usually it's going to use a certain default for the bandwidth. There are some rules of thumb to decide on a bandwidth, but it's again a good idea to play a little bit with bandwidth to maybe get a better picture of what really is going on, or to uncover certain details that are just being hidden in the data. So again, just try to play a little bit with it to see what happens. So in our case, again, we had here longitude and latitude. And if we decrease the bandwidth in this case, and it's 0.001, we see the result. It looks like flames, right? There's a lot of peaks everywhere, and it's essentially giving us a model that represents too much the actual data we have, but not so much the underlying reality, probably. So it's kind of overfit into the data we have. And it might look like there's something going on, like peaks around here and there, but those are just artifacts of the visualization. So very often we want to just change the bandwidth in this case, and if we increase it, it might look something like this, which looks a lot nicer, but we are missing those peaks we had around there and around there. So again, there are sensible defaults for this. Just, usually you can trust your software, but it's a good idea to just play around a little bit, see what happens. And we also have something called the box plot, which is a very simple visualization to get a rough picture, a big picture of a distribution. And it's very useful to judge the asymmetry about the median. So is the distribution kind of symmetric, or is it skewed towards high values or low values? How it looks like is like this. So over the x-axis, again, we have the different values, and then we have a box and then different points. So the central line in the box represents the median. So that is the second quartile. And then we have just what is the first quantile and the third quantile. So we know that within this box, we have 50% or the central 50% of the observations. 25% are going to be lower, 25% are going to be higher. And then we have these points that represent outliers. So each of those is one observation that is considered an outlier. And in this case, it's considered an outlier if it's larger than 1.5 times the interquartile range, farther from the third quartile. So the distance from here to there is 1.5 times the interquartile range. And we could also have the same in this direction. If it's farther than 1.5 times the interquartile range, it's considered to be an outlier. Now, this is completely arbitrary. It's a rule of thumb, but again, It's going to give us a rough picture of what the data looks like, and if we have too many outliers, asymmetries, etc. And finally, we have something called the violin plot, which looks a lot like a box plot, but instead of plotting a box and the points for the outliers, it's just plotting a density that is kind of mirrored along the y-axis. So we have here just a regular density plot, and then it's mirrored. So it has this shape like a violin. So it's the same idea as a box plot, but showing densities instead of the interquartile ranges and outliers.